Uh, Thank you, everyone. I am Christophe Diot from Google, and I had the pleasure to organize this session where a fireside chat where Nick McKeown, professor at Stanford, will interview Amin Vahdat, who is a VP and fellow at Google. So I'm not going to introduce everyone. Amin and Nick are well known in the community. You can go online, and I think that Nick will do a little bit of an introduction. And I want to thank them both for this session. Uh, I, uh, I want to thank Ned Foster too, who has accepted to be our safety net, to be the backup person in case there is an internet problem for one of us. So thanks everyone, and I give the floor to Nick to start the session.
Thank you so much, Christophe. So Amin and we've known each other since grad school, when we overlapped in Berkeley in the early 1990s. I actually think that we met before the very first web browser was created. I was a PhD student in networking, which at the time was really more of an EE discipline in those days. And he was more in distributed systems, which was in CS, of course. And we met as part of the Network of Workstations project at Berkeley. And I've had the great pleasure to know Amin ever since, particularly after he moved to the Bay Area to join Google in, I think it was 2010. Since then, as many of you know, his rise at Google has been, as a member of the executive team, has been nothing short of meteoric. He's now a VP, part of the executive team at Google, and is responsible for the machine learning systems and cloud AI teams, which include Google's cloud network infrastructure, their ML hardware, and their chips. He's also responsible for systems research at Google. So like many of you joining us today, I have had the pleasure of reading many of Amin's very influential papers in networking systems. And his team at Google, as you know, has invented and deployed many new ways to build big planetary scale systems. And after Google has these systems running in production for a while, they typically publish their experience and share it with the wider world. So when you've known someone in their professional career for a very long time, I've known Amin for at least 30 years, you sometimes realize that you actually don't know their origin story. Do they come from a family of academics, researchers, scientists, or are they a pioneer in their family? Was their upbringing one of privilege and entitlement, or did they forge their own path? Were they always destined to be a researcher, a professor, an inventor, or an executive? You probably don't know about this about Amin. And I realized that actually until recently, I didn't either. So I'm going to start by asking him about his background, ask him if he'll share that with us, and then see if we can understand a little bit more about how this shaped him, his career path, his choices, the ups and downs along the way, as well as how he sees the world of networking systems today. I think you're going to find that he's very thoughtful and reflective for sure. And like many of the best leaders in our industry, he's deeply technical and always humble. So, Amin, welcome. It's very good to see you.
It's terrific to see you, Nick. It's such a privilege to be here with everyone in the audience, and of course with yourself. Thank you to Christophe and team for organizing this in the network channel. The chance to speak with you in this setting has been something I've been really looking forward to. As you mentioned, Nick, we go back 30 years. What you didn't say is that I was a lowly junior grad student that you took some kindness to. I mean, you were a superstar. I think it's an understatement to say, even as a grad student at Berkeley. Many of us wondered in awe at, oh my gosh, this soon-to-be professor at Stanford. And you set quite the example for many of us, an inspiration for many of us. And it's been a privilege to actually work with you and learn from you for the intervening 30 years. I remember when I was a professor at UC San Diego, and you called me up and said, hey, we have these switches And they run this protocol called OpenFlow. And I think you might want some of them at UC San Diego for your research. We'll maybe talk about that more later. But so many times, so many moments where you've been such a inspiration to me. So really excited to have this opportunity. Origin story. I will try to keep it brief. I guess, that's something that one could talk about for a long time. I am originally from Iran. My family and I immigrated here when I was 6 years old. And I actually wonder about that, in that, my father and mother showed up with 2 kids and 4 suitcases at SFO from Iran. No family, no hotel reservations, literally no job, no education, actually. I'm the first person from my family to go to a university. Both my brothers, second brother was born here in the U.S., followed in those footsteps as well. But I wonder at the courage that they had, because actually they were doing reasonably well, let's say, in Iran, but they wanted something more for their children. And to show up not speaking the language, not having any family, not having any, making the reservations at the hotel, finding an apartment, etc., really inspiring to me in terms of what I think something closer to true courage looks like. I had the privilege of going to Berkeley as an undergrad, as a grad, seeing people like yourself, but also the faculty there. You know this very well, Nick. The faculty there, some of the ones, my advisor, Tom Anderson, Dave Patterson, David Culler, Eric Brewer, so many others. They made the job something that you wanted to do. And that was true of me. I mean, as an undergrad, I decided, you know what, I have to be a professor. I have to go get a PhD. I have to be a professor. What an amazing job. So that's a brief snippet, I guess, of the background.
Thanks ever so much for sharing with us. I think that many people that just don't know that about you. So how did that shape who you are today?
That's a great question. I mean, the best version of it is I'm a huge fan of the power of education. I'm a huge believer in growth mentality. In other words, for me, I think if there's one thing that I like to tell anybody who'll listen is we can all improve radically and dramatically. I would say to you, Nick, if you thought back to when you first met me 30 years ago, I hope that I've improved dramatically in those intervening 30 years. And in other words, if people were to take a static mindset of me in my early 20s, in my early 30s, I'll admit it, even early 40s, I've grown, and I have that same faith in others. So in other words, for me, that optimism and that belief that people can and will and want to continuously improve is really, really important to me. And the power of education. In other words, the reason I wanted to be a professor is I think back at how much my life changed, my opportunities and my family's opportunities changed as a result of education. The part of maybe I didn't share is my father actually went back and got his degree here in the U.S. He got it only a few years before I did, actually, but he did. And that was also an inspiration.
That's an incredible story. That's an incredible story. So when we parted ways when we were in Berkeley, you went off to Duke as an assistant professor and then on to UC San Diego, and you stayed there until you joined Google. So do you remember what your aspirations and interests were at the time? Did you know you were optimizing for an academic career to be a professor? Or did you kind of have this hunch that maybe you'd go off and become an executive at a big firm like Google?
I loved being a professor. And you know this, Nick, but and I miss a lot about being a professor, actually. So in other words, my goal, my belief was to always be a professor and to, as you said, optimize for that outcome. I came to Google on a one-year sabbatical, and it was, that was Google knew that, I knew that. The goal was to be there for a year, learn a lot. I'd never had a job in industry. The closest I'd come was at Intel Research Lab for 3 months, and then some internships at Xerox PARC, both research labs. So in other words, this was my opportunity to hopefully become a better professor as a result of the learning. I was very fortunate at the time I joined Google. The story I like to tell is when I joined, if you look at the org chart, then there were 7 people between me and the CEO. And all 7 of them were PhDs in computer science. Including Eric Schmidt, who actually some may not know did Lex for his PhD dissertation, right, a cornerstone of compiler technology in the early 70s at Berkeley. So the point is, I landed in maybe one of the only spots in industry where a wild-eyed, a little bit stubborn professor, academic, could have any hope of modest success.
I can confirm you're a little bit stubborn at that time. I think we all were, because I think that when we're younger, we think we know everything, and maybe that danger does persist. But
yes.
Yeah, after a while, you realize, of course, that we don't. I think the older we get, the more we realize we don't know. But
Very true.
When you joined Google back in 2010, it must have seemed really like a huge place. And very daunting. So, if there are any university presidents around the world listening right now, I think actually Amin said that he really missed being a professor. So you should start recruiting him really hard. But when you joined Google, you brought along your ideas with you. You had lots of ideas about data center network topologies, of course, that we all know your work, SDN and optical switching. But what was Google networking like at that time? How did you approach evolving and changing it over time?
It was a really exciting time, of course, in academia, but in networking, but also at Google. In other words, Google's mission, organizing the world's information and making it universally accessible and useful, really did, at least in part, reduce to an infrastructure problem. And I mean, if you looked at the history of Google prior to, let's say, 2010, the breakthroughs in distributed computing, GFS, MapReduce, Bigtable, Borg, system after system of large-scale distributed infrastructure. The thing that maybe, if I'm giving too much credit to it, but probably not too much credit, networking tied it all together. In other words, there was this understanding that having a large-scale, tens of thousands of servers, ports, high bandwidth network that was cost effective, that was reliable, that could evolve, was central to the success of the distributed systems infrastructure that in turn powered things like search and YouTube and ads and all the services on top. So it was a big place, but it was also one, and I think still is, that is really focused on infrastructure as a differentiator. And the ability to do things that perhaps because of scale, because of ease of use, because of efficiency, weren't possible elsewhere. That was the goal.
And so if you look back on from 14 years later today, back to 2010, but let's set aside AI and machine learning for a moment.
Yes.
They came along and changed the focus. We'll come to that a bit later. But if you look back from a networking as we thought of it at that time, what do you think were the biggest changes and advances in networking that happened, both inside and outside of the data center, and perhaps both in private and public networks, if you have a perspective?
We were so at Google, the teams were already to give very well-deserved credit to the teams. There was already understanding of the need for really scaling out the network across 4 dimensions. All right, there was the data center network. There was basically, think of it as the building scale network. We talk about warehouse scale computers at Google, tens of thousands of servers in a building, and that needed to be is essentially, let's say, non-blocking at building scale. Well, and the way I described it to the way that others describe it perhaps is we should be able to support any-to-any computation across the entire data center building. And you shouldn't be able to notice modulo, perhaps, latency. But even today, and maybe we'll talk about this more later, unfortunately, within a building, you can't distinguish much between latency within a rack, within a row, within a building. Now, you and I probably both think that should change moving forward, but still, to first order, it was the bandwidth that mattered within the building. Now, our campuses consist of many buildings, and you'd actually like to be able to connect them regionally. So we needed a high-speed, efficient, scalable regional network. That was dimension 2. We already had many campuses across the world, and a growing number of them. So we needed an interconnect, a private WAN, to connect them together. And then, of course, delivering content to even back then, certainly high hundreds of millions of users, perhaps coming up on billions of users, and certainly today, billions of users across the planet. So data center network, regional network, private WAN, and public WAN, the internet, and really delivering the highest levels of reliability, lowest levels of latency, highest levels of bandwidth across the board, were known to be enablers for the entire company. I mean, we have some well-known rules of thumb internally, how much value each millisecond of latency delivers to users for web search, and things like that.
I see. And so your particular vantage point that you had at Google and the scale, in some ways, things have reversed where you got started because of the public internet, and nowadays the public internet in some ways is relatively small compared to the kind of scale of networks that you manage and run. And so from your vantage point and from that place, where you operate as an autonomous system, it's not clear whether, at that kind of scale, how that upsets the balance of the internet as a whole. What thoughts on that?
Yeah, great point. So in other words, one of the real enabling things about being at Google was that within the autonomous system, we could control the host endpoints communicating with one another and the network in between. In other words, and this was, work in the end tremendously inspired by yourself and others around software-defined networking. In other words, I had a hypothesis coming at it, as you said, from a distributed systems background, that actually, if you could start, so let me step back. I became interested in in networking and internet protocols because of their beauty. In other words, the fact that you could have in a completely decentralized manner, no centralized control, protocols like routing, protocols like TCP work, and you could grow the network incrementally in, again, an entirely decentralized manner to the point of success that it had achieved was stunning. The protocols were beautiful, are beautiful. In other words, if you think about them and you try to improve them, I mean, just from an intellectual perspective, just tremendously fascinating. At the same time, somewhat constraining, because the problem definition is so hard. Right? You don't have full state, right? Decentralized states, pairwise communication, eventual consistency, etc. These are super challenging constraints to place, and that's why so many people are attracted to the problems, because improving on them, and if you want, solving them, are super hard. Within Google, within an autonomous system, so it could be other companies as well, the hypothesis I had, again, inspired by SDN and in the end putting it into effect, was actually, if you were to build it without starting with internet protocols, a better way to do it from a performance and reliability perspective would be around logically centralized control. And those were the ideas that we applied to our private WAN before, to our data center network, Jupiter, which also actually extended to our regional network as well between B4 and Jupiter. So the notion of being able to plan the network centrally, manage it centrally, again, under logical control, even manage traffic, perform traffic engineering centrally, actively, gave us significant improvements in efficiency and reliability, and in the end also in cost.
I mean, these kind of nuances in a way, or these experiences that you get only from operating at a big scale, to be honest, they often don't really come across in the limited format of a research paper. You've only got 15 pages or something like that. And so I expect there's lots of things that have surprised you, but I'm wondering if you can think of something that will probably surprise us, maybe kind of common knowledge to you and the people that you work with, but something that wouldn't really come out in those research papers. You think of anything?
Yes, I mean, a number of them, but I would say the criticality of reliability and the criticality of network evolution and iteration speed. We've tried to cover this in some of our research papers, but actually I would say that one of the keys to our success has been that we can upgrade our network on software time. Like, we talk about being able to push updates to our controllers, let's say our routing controllers, our network management tools. The goal is on a weekly basis. Maybe we don't always make it, but if you look at the state of the art, maybe even today externally, network maintenance operations are annually in many cases. So now think in terms of everybody's equally smart. And I truly believe that, like going back to growth mentality. If you can iterate on a problem once a week, and I can iterate on a problem once a year.
Yeah, absolutely.
Very, very quickly, and we're equally smart, right, and equally observant. Who's going to come up with the superior solution, right? Pretty quickly. So the software control and the centralized control and the orchestration to drive that is absolutely key to the success. So we can ship features many times a year, and we can ship them independently, because we also wound up with a architecture described again in some of our papers where there were, I don't want to call them micro services. They're not quite microservices, but they're at least mini services. In other words, we didn't have a monolithic controller that all software engineers had to contribute to simultaneously. We had subservices that could be iterated on and released independently.
So I can't, overemphasize too much for people on the call who are relatively new to networking, that, at the time that this journey started, maybe in the mid 2000s, network management, network control, even if I mentioned those, you'd be kind of yawning, right? They were topics that really didn't have much attention paid to them. Even the networking companies, particularly the equipment companies, saw them as a distraction and didn't really have good options that were available. So what Amin is talking about in terms of that ability to manage control and the reliability that comes with it, were all considered kind of not particularly interesting academic topics at the time. So, you and others who have shared, I have to give due credit to Microsoft here too, I think, in terms of, the amount that they've shared with the world, and Facebook too, as in the things that they've learned and the important problems to solve in this area. So if you could change one thing about networking, or how we as a community think about networking, what would it be?
So I think that iteration speed is one of them. The criticality. I'm going to cheat, Nick. I'm sorry. I'm going to name two. But to me, the related one is reliability, and probably the thing that actually, looking back, I'm most proud of with some of our work and networking, is that when we started before our wide area private WAN, we had to sell it as the cheap 99% reliable network that essentially you could copy traffic from one place to another, and it would be super inexpensive. But no one believed that they could count on it, right? A bunch of software engineers in the networking team building a network system. Why would you count? You couldn't put production services on it, was the belief. A number of years later, and it did take more than one, it did take more than two, our networks were more reliable than what you could build from quote unquote production gear. And in fact, the ideas from our systems wound up being incorporated into production systems. So today, our internal systems deliver higher levels of reliability than what you can get otherwise. And that's something that I can't emphasize the importance of enough in terms of the network community. And so focusing on that aspect of the work is really, really important. Looking forward, I would say the biggest thing, and I do see evidence of this actually already happening in the network research community, is focusing on the end-to-end. In other words, in the end, the network is a component in a larger scale system. So the end-to-end thinking and protocol design has been there for 40 years at this point, or more. And the notion of extending things all the way to the application view, really, really important. And so in other words, as we think about services that run on our network, how would we think about how we would drive design and efficiencies that actually impact the application? In other words, not in terms of necessarily max-min fairness, or not necessarily in terms of cost per bit, but in terms of delivered application goodput. In other words, there are real opportunities to make our network better, but they're in service of applications and services that run on top of them. What are those higher level metrics that we can improve?
As you're saying these things that really come as a consequence of you're operating at scale, it's tough for the rest of us, right? It's tough for the researchers. It's tough for those of us that don't have a network of the scale that you have. I wouldn't know how to operate one if I did, but it leaves us sometimes wondering how it is that we can contribute and take part. And I want to ask a question a little bit along these lines. It's a sort of a cheeky segue into a question of something that we've not always agreed on. I mean, just to set the stage a little bit, one of the things I've always admired about you is that while we usually agree on the overall goals at a sort of a high level, we're able to disagree agreeably on the details, and we often have, and we debate and discuss and duke it out on some of the tactics. And one example is I've often given you a hard time that Google should get more involved in open source projects to open up the infrastructure to the broader ecosystem, to researchers, not only to let people see and observe and learn from what you're learning, but actually to create an ecosystem where you, your competitors, your suppliers, everybody can be part of this ecosystem, whether it's for switch operating systems, network hypervisors, control planes, and so on.
Yes.
And I've always felt that networking companies, that when they do create open source infrastructure, it can, not always, it can transform the industry. We've seen examples in Linux, ePPF, DPDK, and we've seen OpenFlow, of course, OVS, Sonic, P4. You've always pointed to the difficulties of disentangling your software from the Google dependencies, and of course the cost of the opportunity cost of devoting engineers to work on that. Help us understand a little bit about that struggle, that balance, and how you feel about it.
Yeah, it's a great question, Nick. And I remember many walks that we've been on debating this question. And I'd like to say that this is one where there's rarely a binary situation, but this is one where you've been more right than me over the years. Though I have taken all your feedback to heart over the years. But talking about some of the challenges that we face, one of the great things, but also strengths become weaknesses at Google, is that we have a monorepository. Mm-hmm. And what that means is that all of our code is in one code base in the end. In other words, it's not that there is the network controller code that is independent. Let me give a very simple example. You might imagine that we really care about a reliable leader election for our controllers.
Yeah.
And you might further imagine, and maybe some people have read the paper on Chubby. It's now somewhat dated at this point. I think it was 2006 or so. So maybe there's newer versions of it, et cetera. But you might imagine that we then rely on Chubby leader election in a way that is partially clean from an API perspective, but one that might also actually be deeply intertwined with our code. As one example, we might rely on a key value store. We might rely on NoSQL, but still database-like table abstraction. These are all things that if we're building a controller, let's say a SDN controller at Google, we might go and build upon, because actually getting those things right is super tough. It takes a lot of effort, takes a lot of years. And when some other team has already gotten it right, it really behooves us to leverage them. Now, taking those same things and then trying to open source our infrastructure, our let's say, SDN controller is a challenge. And we would take a tremendous amount of work, actually, to do that disentanglement. Totally possible and likely worth it. In other words, one could say, well, there is, I don't know, Zookeeper or some other leader election protocol. How would you abstract your code to be able to be pluggable, but also over time with Chubby software releases, if we're using Chubby internally, or its evolution and Zookeeper simultaneously?
Mm-hmm. Can you think of a way that would get us in that direction over time? You know, with the way that you and some of the other companies could sort of set the path to be able to go in that direction, or has it become so entangled at this point? There's really kind of monstrous undertaking that couldn't really be done.
Yeah, and again, if I may, and I'm just going to speak very, very openly, maybe too openly, the open source efforts oftentimes get bogged down in political. Not political might not be the right word, but in the end, the goals of individual companies.
Yes.
So in other words, we would then, and you've experienced this more than I have, Nick, but in the end, if we could spend our time saying, hey, here's the right technical API, which many of us would love to do, but then the right technical API might not be what is best for every company in the world. I'm not going to, there's no example, but I think you and maybe others know some examples that we could draw upon over the years for this. So now you need a large number of humans to drive those discussions. And without naming companies, you can imagine that there are, at some companies, dozens or even hundreds of people whose full-time job it is to drive these discussions, whether it's at IEEE or IETF or somewhere else.
Yeah.
We've not, at Google, candidly, we've not been set up for that kind of engagement traditionally.
So I'll take it as my job then to continue to give you a hard time. But
please, and by the way, I do believe, like in other words, you and I talked about this earlier. I wish we had our controller in open source.
You know, you're staying on the topic of data centers. Your 2008 SIGCOMM paper on a scalable commodity data center network architecture, it really questioned how data center networks were being built at that time. You know, they were using increasingly complex, expensive switches as you go up the hierarchy of the tiers of the network. And much as the public internet was built at the time and often still is today. And you showed us that you could instead build a data center using identical commodity Ethernet switches at every layer, arranged as a fat tree. So the paper taught everyone how to do it, and soon pretty much every big hyperscaler was built pretty much that way. And I'm curious, you know, if we look back on that more than a decade later, this key result of being able to build large networks from a bunch of identical single switch ASICs. Heck, I even spent a decade trying to build them myself, and so I'm was part of that effort. It's really changed the industry for sure in a huge way, right? All of the emphasis on those single switch ASIC chips, that's where all the investment is, or pretty much all the investment. Did you think back in 2008 that were you deliberately trying to have an impact on the industry? Was it just an academic paper that was published and then move on to the next project? Can you put yourself back in the shoes then? Because I think it could be quite helpful to people who are in an earlier stage of their research career to know this balance between doing something which is just purely academic to publish versus something which has let's face it, an evangelistic part, an evangelism component to it.
The evangelism component has been really important to me, and it's something, again, Nick, and I'm not just saying this because we're talking here, that I learned from yourself. I learned from the faculty I worked with at Berkeley and Washington and elsewhere. In other words, I think for many of us in systems and networking, the goal is impact. In other words, we, of course, maybe not every paper is gonna get there, but our goal is to drive change and drive improvement and drive impact. So I remember that time in 2008 very well. So I will get to your question, but I also want to acknowledge for a moment, and you might not have known it at the time. I think you did, but the work that you and your teams were doing at the time were really foundational. In other words, that Quanta switch that ran OpenFlow, that we actually did wind up getting and installing in our racks, gave us experience with OpenFlow. The work that your team was doing on NetFPGA, something I really encourage everyone to go look at, that essentially showed how you could have a programmable switch under something like, if not exactly like OpenFlow control, was really inspiring. You talked about the challenges of being able to do in an academic setting research that could influence industry. In the end, what we wound up doing was going and buying a modest number of FPGAs, implementing OpenFlow to control them, and showing how you would build a scalable network architecture with a pretty small scale demonstration, certainly by the standards of industry. So what I'll say, looking back to 2008, one of the most formative times in my career. I can say I was just with my students, of course, and colleagues. Just it was that time when you woke up every day, when you came into work every day, knowing that you were working on something that for you was really, really exciting. I'd had that feeling, been fortunate to have that feeling a few times in my career, a few times since as well. But, looking at myself as an academic then, the last couple of times I had a similar feeling. My papers got rejected. Those papers I was writing, and then actually maybe they got rejected the second time and the third time as well. Without going into those aspects, those efforts wound up being modestly successful anyway, despite the rejection. But even this paper, and if I look at it, and if I look at the reviews that we got from SIGCOMM that year, it almost got rejected. Like, it was not people were not praising us for our incredible work or saying slam dunk, strong accept, this is the greatest thing we've ever read. It was clearly discussed heavily, judging by the reviews. So we were fortunate. But yes, absolutely, we were driving for impact. we were taking these ideas to companies, actually, as well, as trying to convince them to adopt them, and hoping that the others would see value in the ideas that we were pursuing at the time.
I think we both can look back and benefited enormously from those incredible professors that we had at Berkeley. Mm-hmm. And I look with great admiration Dave Patterson, as you mentioned earlier, and Tom Anderson and David Culler, and my own professor, Praveen Varaya and Jean Morin.
Yes.
Between them, just always impact. And so if you think about the impact that you can have, it doesn't distinguish the academic value from the evangelism, because you're trying to have an impact, which in many ways is to influence others to follow that same idea. And so I think we both had the benefit of learning at the feet of the same experts. So, exactly. Along this path of the things that we've learned, or things that we've, the views that we have, I personally think that we lost a decade or two in networking because we believed, almost like a religion, that resequencing packets is a bad idea or is expensive. And I strongly disagree with the view that it's expensive. I've personally built many NICs and switches and software stacks that, not switches, NICs and software stacks that cheaply and pretty easily resequence packets at the destination. I think we all know that's quite doable. I personally believe that we should allow the network to missequence if it helps it perform better or be more efficient, more fault tolerant, more bandwidth, more paths, less congestion. But would you agree? And I mean, I know I'm asking this suspecting that you do, but do you think that we're finally on a different path, as though we've kind of set this aside and standards like UEC is helping us break this?
I would agree, and I do think that it's interesting to me. Some of the follow-on papers to our factory paper on Hedera using optical circuit switch. Helios using optical circuit switching, and Hedera using active management of flows, and basically repathing them on the fly. Some of the biggest resistance in the academic community was, wait a second, you're going to change the path of a flow actively, and hence, isn't that going to mean that some of the packets are going to arrive out of sequence? And the answer was yes. But that's okay. That's not actually the first order or the second order thing that one should worry about. Our results demonstrated that, and actually the relatively rapid adoption of the ideas probably across industry demonstrated that. But there was this period probably between 2005, 2015, where, and probably earlier than 2005 as well, I would say, where conventional wisdom really limited the adoption of some clearly exciting directions. And I hope now we're on the path for adopting them even more. Like, I can tell you that some of the techniques that we use for active reliability management in our networks do cause packet resequencing, and it's well worth it, is the way I would put it.
Yeah. I think we've both discussed many times, there are lots of sort of sacred cows in networking, and you're probably more patient than I am. Many of them drive me nuts. And I wonder which, I'm going to give you a list, actually, and I want to know which ones you agree with. Feel free, of course, to disagree and tell me if your experience is otherwise. But, I feel that there's a myth that it's really difficult to implement many QoS or priority levels in hardware. It's not. It was common to have thousands of QoS levels even 30 years ago. It's not that they're difficult to implement in hardware. It's that we've never really figured out what to do with them. Do you agree? Is there nuance to that?
I do agree that it's not the hardware that's the limiter. I would say that it's the abstraction that we can provide to the developers that's been the limiter. In other words, we have not, and so this to me remains an open research problem. Let's say you had infinite QoS classes, or certainly a very large number. How would you make use of them in a way that's meaningful to the application? And there's been some work down this path, but frankly, at Google, this is something we've struggled with, because one should not underestimate the importance of simplicity and simplification in terms of the abstraction that you would like the network to provide to the developer. So, for example, if you were to ask the developer, hey, for every TCP connection or for every RPC, you can provide a number between 1 and a billion, right? With higher number being better or something. Would they really know how to manage that in a meaningful way? And then actually in a non-brittle way. One could imagine that over time, they'd get it's not that they get it wrong. It's what decisions that they made earlier in the life cycle of the code become dated. And now you have priority inversions unwittingly, etc. Whereas you would have been better off just saying everything's the same and get it there quickly.
Another sacred cow that we tend to think of that formal verification of networks is too hard. We should leave it to the theoreticians. So we should leave it to the CS theorists. And this is a conversation I've often had with you, with Nate Foster, with Jen Rexford, and the belief that what really gets in the way is having accurate models of each piece of hardware, software, and they're generally either ill-defined. Of course, they're generally deterministic, but their definition is not available to us in a way that we could model or verify. And I always thought that if we could make it standard practice that every ASIC or forwarding software came with an accurate mathematical model or a formal model that was an executable model, we could build much more robust and verifiable networks. Is it just a pipe dream, or is it something that I know you've given a lot of thought to this?
It's I think, far from a pipe dream, and I think that thanks to the work of a number of people, including yourself and Nate and many others, we've made a tremendous amount of progress. In other words, again, it has. I think that you should be proud, Nick, even though impatience is a virtue in a number of cases, of how much progress we've made. So I think we're much further along in terms of the hardware elements being verifiable, and candidly. And you know this better than anybody, how we do, let's say, hardware development of network elements at Google relies on, I won't say mathematically provable model of correctness, but there are reference models very, very close to the hardware that we use to verify implementation in fairly complex settings ahead of, let's say, tape out of the elements. So huge progress, I would say, over the past decade plus here. The open question is the vast complexity of the software systems that run on top of them, the distributed protocols, essentially routing, congestion control, etc. Those are often tougher to get right.
Yeah, I have a lot of my inspiration actually from debates and discussion with George Varghese now at UCLA on this topic. And of course, I also believe, and maybe it's less of a sacred cow than actually a personal religion, that every forwarding device should be programmable, of course, and that its owner, you and your team, should be able to decide what it does.
Yes, and so we've benefited tremendously from this, and I think that, again, if you look at what obviously you've done some of the absolutely most seminal work in all of academia and industry with programmable switching. I mean, if we look at the influence that Tofino, Barefoot, P4 have had on the academic community, as well as actually industry, a broad uptake at many companies, it's been stunning. And I would say that, well, maybe religion, but if you look at how programmable all devices are, all the network devices are relative to just 10 years ago. And now you would say, knowing you, Nick, that they don't go nearly far enough, most of them. And I would probably agree. But if you look at where they were 10 years ago to where they are now, the level of programmability is actually impressive on a relative basis. Now, you would say on an absolute basis, whatever, miles to go. And I'd agree, actually. But I do think that we're making incremental good progress there. And I would also agree that there's miles to go.
I'm getting a bit concerned that we're agreeing too much, and that I'm still wandering around looking for something that you can tell me I'm full of crap on or disagree with.
All right, whatever's next, I'm going to disagree with.
All right, let me try something here then. Okay, so do you measure enough in the network?
No. So you're going to say that we measure plenty? I can then disagree. No, we don't measure nearly enough. Telemetry is an absolute weak point.
Let me ask you about latency. You mentioned it earlier. If I sit somewhere and then actually I did it earlier. I always do my round trip tests to a Google DNS server with 8.8.8.8, as I'm sure many people know. And I'm happy when that round trip time is 5 milliseconds. But I know that the speed of light delay is probably well less than a millisecond most of the places that.
That's right.
Where did all that time go? Is it you? Is it your team? Is it the intervening network? Where should we look to be pointing the finger?
It's 4 milliseconds by 1,000 cuts. Is really what it. You're right. It should be a millisecond, and everybody takes their 4 microsecond tax, and they don't worry about it because it's. Because there's no dominant factor. This is the problem. The routers are going to do some queuing, but lots and lots of reasons. I think that the key question is actually, what would we gain if it were 2 milliseconds? Or 1 millisecond. And again, we have some answers for that at Google from an end-to-end perspective. But for most of the developed world, I would say actually internet latency is pretty good at this point, actually. So I would say that actually the real opportunity is within the data center and within the region. So the fact to me, maybe this is a small disagreement, the real opportunity on latency is being able to take advantage of the fact that you are less than a microsecond away from a server in the same rack. And that you're maybe less than 10 microseconds away from across the building. Like you said, speed of light to your DNS server is maybe a millisecond. Speed of light to a server across the building, maybe it's 10 microseconds. And yet, why is it that developers, when they are thinking in terms of what an RPC takes within the same data center, still think in terms of a millisecond? And the other addition I would have, and there's been some nice literature on this, is variability. In other words, if I look at modern tightly coupled distributed computation, the killer is actually not the absolute latency. It is the tail and the straggler. So for the increasingly synchronous computation that we have in data centers, latency matters as much as bandwidth for actually the speed of the computation end to end. But that variability is absolutely a killer. Going back to your question on telemetry, finding the source of that straggler is arduous task, because we don't have the visibility and the telemetry that we need to be able to say, here is that one misconfigured switch, or here is that one server that actually is running slower than all the other 1,000 servers in the computation for whatever reason, etc. We find it eventually, but it takes a huge amount of effort.
Just before I move on to the next question, I did want to echo a comment that Christophe just wrote in the chat. If anybody has questions, we're running to 90 minutes and we're almost 60 minutes in. So the last 30 minutes or so, we'll probably start at about 5 minutes past the hour. We're going to start taking questions from the audience. So the roughly 300 people that are out there, please weigh in with your questions and we'll do our best to read through those and ask those.
Yeah.
And so we need to talk about AI and ML. Clearly, it's the elephant in the room. Some people would say that it's going to be the elephant in the room that really changes the entire field. Others say it's got a lot of hype to it. I'm sure there's an element of both at the moment, but it's clearly changing it's causing an enormous change in focus for Google and your competitors, and with these enormous foundational training models and vast numbers of inference engines. Google's charted its own course with the TPU. And in general, I'm kind of curious, and I think we'd all love to know how you think networking has changed already because of these systems, and what are the requirements that these systems bring?
It is very sincerely the most exciting time in infrastructure and in networking since I think the rise of internet services 5 years ago, plus minus. And I would say the network has already dramatically changed. And the point that we were discussing earlier around really low latency, tightly coupled communication is one example of that. I would say TPUs, and there are analogies with GPUs, but I know TPUs the best, so I'll talk about them, really taught me a lesson as we developed them at Google 10 years ago. Because, conventional wisdom was, if you're ever going to do network interconnect, we knew what the name of the technology was that you were going to use. It was going to be Ethernet. And we knew that you would build a hierarchical switch topology. I mean, me more than anyone would say you would build a hierarchical switch topology to interconnect the accelerators together, and you were going to use Ethernet to do it. And yet we decided, for good reason, to actually build our own point-to-point non-switched Taurus network to connect our TPUs together. leveraging something that was an Ethernet called ICI for us, Interchip Interconnect, designed not to support IP. It doesn't. Not to support TCP. It doesn't. But to support essentially memory transfer protocol. So from high bandwidth memory to high bandwidth memory, TPU to TPU, essentially the goal of the network was to support parameter distribution and backpropagate errors from among the different TPUs as they were carrying out this highly synchronous, tightly coupled computation. And the role of the network can't be understated. You see NVIDIA going down, let's say, similar paths. I'm not necessarily an expert with NVLink as a non-Ethernet protocol designed to connect their GPUs together. So you talk about sacred cows. This was breaking all the rules in terms of how you would do networking and all conventional wisdom, because there was a fundamentally new style of computation. In other words, the use case was radically different.
Sorry to interrupt, but do you think that this distinction of scale up and scale out networks will go away over the long time scale? Perhaps all becoming closer to Ethernet actually in technology rather than just in name.
Yeah, it's a great question. I do see Ethernet as always. I mean, Ethernet is, and congratulations to Bob Metcalf for his Turing Award. I had a chance to hear his excellent acceptance speech. And it is a remarkably resilient protocol and technology over a 50 plus year period at this point in time. I do think that I hope the convergence happens, actually, because having to manage two network technologies, et cetera, is problematic. But even more so, one of my, if you mentioned some of your religious goals in networking, one of mine is to bring the power of low latency, tightly coupled communication to general purpose compute. Right? In other words, I talked about how RPCs shouldn't be counted on as being a millisecond. Well, if we can bring the best of, let's say, ML style computing to general purpose compute via a converged network and a leaner stack, could we get to a place where we can leverage the capabilities that ML compute, TPUs, GPUs must, it's a requirement, there's no option, it's a necessity, and bring those to general purpose computation? That would be amazing. The other bit I'll note is that at Google and elsewhere, in the end, if you look at a TPU pod today, it's 8,960 chips, so massive scale, connected via this ICI network, goes pretty far. It's not big enough. So we're on record as showing us how we still have to use a data center network, our Jupyter network, and even our regional network, our building scale network, to connect these individual 8,960 chip pods together to support the largest scale training workloads that we do and must support.
So your interest in optical switching really came to life in CPU networks, but now we see that Google is using it for using optical switches to connect together clusters of TPUs. And this has generated a huge amount of buzz and interest, and I can't tell you how many times a week I get calls from venture capitalists or people who are thinking of investing or starting companies that were in optical switching. It's like the buzz term of the year. And there's lots of research papers, lots of startups and so on. How do you see this technology evolving, and what problems still need solving?
Yeah, and again, it's a really gratifying time in my career, and the pitch I'll make there is to gratitude of my colleagues in the electrical and computer engineering department. You were talking about networking starting and continuing to be an EE field. Those days in 2009, 2010, when I was learning the fundamentals of optics and optical communication and what was possible with optical circuit switching. But then the pitch I'll make is the sort of cross-team, cross-discipline collaboration leading to some really exciting ideas around optical circuit switching for network performance, for network evolution. And what's been even maybe most fun is then seeing how, in a really unexpected way, I mean, we had no idea about large-scale ML compute at the time, it would get picked up for ML supercomputing, ML computing. I do think that it'll play an increasing role for a range of reasons, including reliability, but also, I mean, the fundamental observation that many have and why many, I think, are excited about optical technologies here is twofold. One, increasingly, we're going to have to go native optical off the chip, off the compute elements. In other words, now when, we don't know for sure, but it does seem like it's coming. And that's part one. Part two, the communication patterns of ML compute is predictable and very regular and runs for hours, days, weeks in some cases. So in other words, if you know the biggest challenge for adopting optical circuit switching is the reconfiguration time and reacting to dynamics in communication. If you know what the dynamics in communication are, because you wrote the compiler or whatever, you compiled the code, there's just tremendous opportunity moving forward to being able to do a perfect job of predicting when the bursts of communication are going to come, because you know what the computation is.
Absolutely, that sounds like a great observation. I think it's going to trigger lots of thoughts from people listening here today. Staying on the topic of optics for a moment, you said that it's been a long time coming. Yeah, I can remember, and I'm sure you do. In the early days of the internet, video was going to be the killer app, and everybody talked about it being 3 to 5 years over the horizon. It was all 3 to 5 years over horizon, and then suddenly 2006 came along. YouTube and Netflix both took off, and almost overnight that prediction came true. And I have a suspicion that integrated optics and co-packaged optics, it's been predicted that it'll be here 3 to 5 years away for about the last 30 years. Many people are predicting that time is now, and that it's going to hit the big time too, very soon now, on GPUs, switches, maybe TPUs, CPUs, and even between chiplets inside a package. What do you think?
I think that we're almost to that 3 to 5 year tipping point. So I do think, I don't know if it's 2006 today in 2024, but it's not too far from 2006. I think that we're seeing just how hard it is to go from 200 gig to 400 gig in terms of copper, just how exotic some of the PC boards essentially are having to become to support copper at this transmission. Breakthroughs in driving down the cost and power of optics that are coming actually at a pretty fast and furious pace. So I think, and as you know, I've been talking about this for some time. It's been on the verge for 20 plus years, longer probably. I do think that we're actually just about there.
I'm going to take a pause for a moment. I'm going to take some questions from the floor, some of the questions that people have asked. And then I've got a couple more questions I'm going to come back to at the end. And just to remind everybody, you can enter your questions in the Q&A chat. And I'll do that probably until about 25 minutes past the hour, and then I'll pop in a few more questions to Amin of my own just to sort of wrap up. So the first one, and actually maybe I can ask as well Christophe and Nate, who are both reading these questions and have probably read through them more than I have because I'm not so good at multitasking. I'll ask one, and then maybe Christophe, you can ask the next one, and then Nate from the ones that are on the list here. So the first question is, what are the top 2 issues that AI and ML brings challenges to traditional networking and protocols?
Great question. We talked about a number of these in that the latency, the bandwidth, and the cost considerations are just radically different. So in other words, to me, if you look at what a TPU has, essentially it has the bandwidth equivalent of a generation or 2 old Ethernet switch, a high-end Ethernet switch integrated with the compute die. Right? In other words, the amount of bandwidth that you have to get in and out. We talk about a server today maybe having 100 gigabit per second NIC.
Yeah.
Or it's 200 gigabit per second NIC if you're really, really at the bleeding edge. We need greater than, let me say it that way, greater than an order of magnitude more bandwidth than that. So the bandwidth requirements are tremendous. The latency requirements, I mean, in many cases, sub-microsecond is what we should be thinking about. So, and all implemented in hardware. So again, the beautiful thing is, from an opportunity perspective, we can't be thinking in terms of TCP, IP, RPC, et cetera. There's no Linux stack running on the TPU managing those computation elements. It's really has to be implemented in hardware at the highest speed, the lowest latency, highest level of predictability. Again, if one of these 8,960 chips is going slower than the other, it cascades in milliseconds, slowing everything down.
Mm-hmm. Mm-hmm. Christophe, do you want to ask the next question from the floor?
No, there is a question by Jeremy Leguet, which is related, okay? And the question is, if I can bring it on the top, how much Google Network will have to change to accelerate AI workload? and we plan to do distributed training across multiple regions, model serving at scale, etc. So I think it's very related. And
Google networking has changed significantly over the past decade. In other words, the fun part has been that we actually TPUs have been in production at Google specifically for the task of machine learning training and inference for a decade, and we've done networking again very differently for them, and I would say increasingly different for them. We're already, as I mentioned, training across multiple pods within a data center using our high-speed data center interconnect between buildings. And then going to the point of the question, yes, absolutely, we have to look to extending it to regions, just because, again, you can't strand available compute, is the way I'd put it. So if you have available compute for the task, we have to figure out how to tie it together to go after the biggest, hardest computation challenges.
Nate, do you want to chime in?
Yeah. There's a great question here from Juan Pimento asking about sort of planning the physical network and capacity changes. So you talked a lot about growth mindset and sort of iterating and the value of being able to iterate fast. But this is sort of another dimension of, how do you actually plan where the next data center goes, where the next fiber optic cables go? Can you speak a bit about your approach to that?
Yeah, so let me start with the basics within a building, and you might even think within a region. And actually, that's another unexpected place where optical circuit switching has been a big help, in that optical circuit switching allows us to actually evolve the network in place, so we don't have to get the planning perfect. In other words, what we can say is that we have a backbone of our network that's optically circuit switched, and we can bring in different, we refer to them as super blocks, but think of them as approximately 1,000 port elements that can be heterogeneous over time. And then we can change our mind. We can say, well, actually, that 5-year-old 1,000 port technology, we can replace it incrementally without having to think in terms of what might be 50,000 ports in an entire building. Similar thinking might apply between regions. Now, the planning for AI compute across the planet, super complex. Let me give one example. Sustainable power is really, really important to us. We have commitments, self-imposed, to be net zero, incremental net zero for our power consumption by 2030 at Google, and other companies have similar commitments. So now you can imagine that actually a key determiner for where we would want to place our computing infrastructure is the availability of carbon-free power sources. And that might be limited in different geographies in terms of where exactly you would put it. So that's one of probably 100 considerations that go into placement, one of the more important ones, to be clear, and really capable, fairly substantial team that does this planning. And the planning horizon, by the way, is in some cases up to a decade. If you think about really being able to secure large amounts of space, power, et cetera, for the future.
So Rafael Rosa asks, can you share your thoughts on the role that SmartNICs and DPUs, et cetera, that they play in networking systems today? Maybe share what you think of the sort of the future of ePPF.
Yeah, great question. So SmartNICs, and we refer to them as infrastructure processing units, IPUs, play a central role in our architecture and the deployments. So we have the brand name for our technology at Google is called Titanium. And it's essentially the great thing about IPUs, SmartNICs, et cetera, is that they are really the very definition of a server. In other words, we've increasingly virtualized our servers. And so the identity of the server and the composition of that server is determined by the IPU to really increase the security of our compute infrastructure. So in other words, you can imagine that more and more of our compute control, so that's why we refer to it as an infrastructure processing unit. It's much more than a smart NIC. It happens to be a NIC, a network interface card that connects to the network. It happens to have programmable cores, to Nick's point about the importance of programmability. It happens to have semi-programmable packet forwarding elements. Think of it as in the spirit of Barefoot Switch on the NIC. It's actually known to be actually in collaboration with Intel on a joint product definition together, and actually, again, in production. So bottom line, a really critical part of our infrastructure is this infrastructure processing unit, the very basis for our security and the control of how we manage computation. including for our AI ML infrastructure.
And eBPF?
Yes, eBPF. So this is one that I talked to with the team about. I'm really blown away by eBPF and how successful it's been. Talking back to graduate school, one of our colleagues, Vern Paxson, who's a grad student and then faculty at Berkeley, did with others the Berkeley packet filter. And the community around that over decades has just been stunningly successful. For me, another question that Nick and I could have talked about earlier is, the split between how you do extensible sort of programmability within the kernel, including for networking with eBPF, and then how you do programmability or the specification and programmability within the network with P4. And then others in the industry are also adopting P4 for the NIC side. Really, really interesting. I've talked to Nate about this as well. I would love to see these technologies come together more. I want to call out eBPF has been amazing. Really kudos, and a lot of great research papers as well around it. The capabilities are really impressive. Would love to see how we maybe bifurcate less. In other words, how do we focus more and come together a bit more in terms of the programmability layer or API for these elements? Nick, feel free to jump in on this question too, since you know as much or more than I do here.
I've spent a lot of time thinking about this too. We've talked about it a lot, but the P4 is clearly designed for programmable hardware, and eBPF is designed to fit well with the Linux kernel and developers for software. And we should see our goal collectively as bringing these two things together in a consistent way, so that you can use something like P4 when you need to optimize for the hardware, but for the ease of development where you don't need to do that, eBPF, because it's fantastically flexible and really powerful, and being able to use the best of both. And there is a very high impact piece of research there for somebody to do and demonstrate and show the rest of us how to do that right. So moving on, Christophe, do you have a next question? Putting you on the spot.
Yeah. I have one, and because I imagine that there are many students listening to this fireside chat. I have a question that comes from a student. If you were a PhD student today, let's go back for a while. What would you work on that is not just incremental and yet doesn't require industry level infrastructure?
Yeah, this is a great question. And first, I think, being a PhD student, what an incredible job. I know it can be stressful, but the opportunity is immense. Really, if I were to give you some, what I hope is comforting advice, the goal with your PhD research is not necessarily to have the set of breakthrough papers that redefine industry. As much, it's to get good at framing questions and being able to go about answering them effectively. That to me is the biggest opportunity. And so, and I think that as a PhD graduate, and let's say you're interested in academia, let's say you're interested in industry, either way, people are going to be able to judge you. Your faculty members who are writing letters, the people who are interviewing you, whether it's at a university or at a company, based on your capabilities, and they're not going to judge you for your papers. I know this is maybe this is controversial advice I would give, but I'll say that when I graduated, I had exactly 0 first authored papers. Or when I was interviewing, certainly I had exactly 0 first authored papers. And what I hope, though, is that I had some skills in being able to form questions and answer them and be able to carry out conversations in a meaningful way on the research. So I could give you a list of ideas, but I can almost detect the stress underneath the question. Don't put so much pressure on yourself to have that breakthrough, completely novel, non-incremental industry, leading idea for your paper. That's for your research or your dissertation. That's almost too much pressure for anyone to take on as the expectation.
So Nate, do you want to jump in?
Yeah, actually, I want to kind of piggyback on that question. So, there's a lot of stress in academia as you see these kind of big trends, and ML is a clearly huge disruption, and students kind of swarm into it. Do you see at Google, do you see sort of, is networking attracting sort of top engineers? I mean, you made a case before that this is a really exciting time for infrastructure, a generational change. And I know you've given talks on this, but yeah, kind of what do you see as far as like sort of how our community is doing in attracting the best and brightest, and maybe what pitch would you make to people who are at an early stage for why they might be in this field?
I would say follow your passions, because that's actually going to be the biggest determiner of success. One could say, so in other words, there are people who just love systems, and to me, networking is timeless in its criticality. Not to take anything away from, let's say, compute or from storage infrastructure as well, but networking certainly has a special place in my heart, many people's heart. Over a 50-year time period, the importance of networking hasn't really waned, right? So in other words, in terms of a pitch, the way I'd really put it is, if you're drawn to the style of work, the protocols, it intellectually appeals to you, if you love building, hey, if you're good at theory and you're good at formal methods, and the problem domain appeals, incredible area to be in. But I would say trying to predict what will be the hottest area upon your graduation is, especially for more junior grad students, is a little bit not likely, I think, to result in the best outcome in the long term. That would be my advice. Following your passion.
If I could just agree with you, I mean, it's remarkable, I think, to have, you and Nick, two giants in the field, still here geeking out about fat trees and, packet spraying and all these top topics. So I think the passion for, the core concepts in the field really comes through, and that is what drives any research career.
Yeah, you gotta love it, and that's the most important thing. So in other words, if you say, like me, let's say I'm less good at formal methods, which happens to be true. If I were to say, well, I think in 4 years' time, formal methods is going to be the hottest area for jobs, and I then switch to that, and I'm less good at it, and less passionate about it, probably not the best decision on my part.
I think we're geeking out because we're both sitting here thinking, God, we'd love to be PhD students again.
Yes, absolutely.
Yeah. So you spoke earlier. This is a question from Robbie. I don't know the last name. You spoke of electricity consumption and the net zero impact goals. What plan does Google have to handle the direct impact on that this has, and to support this ambitious data center and network, and now AI and ML growth as well?
Yeah, really important topic, and one that I have a personal interest in, actually. And so I would love to do a plug for a Communications with ACM article that actually Dave Patterson and I and Xiaoyu Ma at Google did, really talking about the importance of metrics in driving the optimization of our work. And we talk about how moving forward, we should be thinking in terms of performance per average watt and performance per CO2e as the basis for how we design and develop our systems. And actually some interesting thought experiments. It's to me, eye-opening in terms of how we would drive our work based on the metrics that we use to evaluate them. So that's one thing that we're doing, is we're really putting power and the criticality of power as a primary consideration, perhaps the primary consideration, in terms of how we judge system design. The other aspect of it is, again, in terms of how we power our infrastructure, the environmental impacts, the carbon consumption, et cetera, associated with it is forefront to our thinking, including our longer term planning. And then finally, I think there are some, maybe going back to the first point, and a great thing from a research perspective, a question to ask and answer for ourselves is, what is the shape of the utility curve between delivered performance and consumed power? I think what we would find, what you would find if you were to take these measurements, is that actually delivered performance is not linear with consumed power. And in fact, it tails off. It might start higher than we want. It might be linear in some zone, but then actually you might, let's say, double power consumption, but only improve performance by 5%. I made that up, but one would probably, if they had that information available to them in some control loop, they would probably actually throttle the power available to a particular computation, not say, hey, I'm not going to throw double the power at this for 5% more throughput. I'll actually finish my training job 5% later. as one example. We're doing those kinds of things at Google. I think there's many such opportunities, related opportunities.
Does this give you sort of an indication that perhaps we will see, as we get hopefully past this manic competition about foundational models, and the biggest foundational model that anybody could train, that as we hopefully sort of converge or settle on that, you would expect to see big opportunities for energy efficiency, big opportunities for improvement?
For sure. And actually we are, I mean, the good news here is that year over year, whether it's algorithms, whether it's energy efficiency of the hardware, whether it's model architecture, there are greater than a factor of 10 improvements that are being driven. So in other words, you could say, I just need as much computation as possible and as much power as possible. But actually, there are lots of other techniques that you would be employing first before saying, I need double the power or I need 10x the power. You'd actually be better off investing in other techniques to get the same outcome, if that makes sense.
Yeah. I'm going to come back to some questions that I have for you just in the last 5 minutes or so that we have, because I just really wanted to go back to a little bit about your own journey, sort of bookend where we started with your own origin story. You know, I'm sure there's many things that you've looked to improve about the way that you work as you've gone through your career. But if you could change one thing about the way that you work today, if you could change one thing, what would it be?
You know, and this is going to sound familiar probably to you, Nick, and maybe many in the audience, but time is our most precious commodity, right? And I think that many of us, in terms of being driven by impact, are there are different kinds of impact. And as we grow older, as I grow older, you know, for me, yes, technical impact is high on the list, but impact on people, individuals, is actually the thing that drives me. I know many of us the most. So I think being even more conscious than I am conscious about how I spend my time, but I think it is all too easy to get in react mode. So if I could change something about how I work, I would be even more conscious about my time allocation and making sure that I'm not spending probably as much time as I am reacting, more time thinking, but intentionally thinking about driving that impact and driving that impact to where it matters, which, yes, technology, but even more so people.
To be a bit more specific then, I'll drill down on this a little bit. I know that I think you have about 9,000 or 10,000 people working for you at Google. And I just imagine that the breadth of topics, and I'm sure that you can't help yourself but try and get as deep as you can on each of the topics. How do you balance that time between, you know, the urgent and then, you know, what specific steps do you take to stay abreast of technology, and how do you go about choosing what that is?
In terms of staying abreast of technology, you know, I still serve on a couple of 3 program committees every year. And in fact, I have some overdue NSDI reviews that I'm sure somebody on this call is going to be pinging me about. Just a few days overdue. I'll be getting to those shortly. And it's a privilege to be able to review and read those papers and gain something from them, as I always do. I make it a point to still try to go to a conference or so a year, but also we have a large number of interns at Google, a large number of relatively recent graduate students at PhDs or whatever you want to say at Google. I actually allocate time to speak to them. And to speak to them, I say, listen to them, because I have a lot to learn from how they think about problems, what they've worked on, what they are working on, etc. So it is but then also, again, with respect to the urgent, I'm also very privileged where I have a lot of capable people in my team who handle, I'm super lucky here, who handle most of the urgent. Every once in a while, I have to jump in on something, but it really is a privilege to be able to dive in, connect the dots, and learn about a range of things. But if you try to cover everything, you'll fail. So it is important to actually make sure you're going deep on one or two things, preferably one, but one or two things at a time.
You're one of relatively few professors I know that made that adaptation and that change from professor to executive. And you know, do you think more people who are academics should consider it and enjoy it? I'm not saying that whether it's a but do you think that generally we tend to think of these worlds as siloed, and that perhaps more people would enjoy the experience? And well, yeah, just curious what you think about that.
I again, thinking in terms of privilege, had a relatively privileged path of being able to work as a mostly individual contributor until recently. I'm not an individual contributor at this point, but that path was for the first bit of it as an individual contributor, where the goals were technical at a place, at a company that really valued the technical work and continues to. So to me, a rule I have, Nick, you and I have talked about this, is I actually never recruit a faculty, ever. Now, sometimes faculty might come to me and say, hey, I'm really interested in okay, we can talk about it. But I actually think that the job of a professor is really, really precious and important. I mean that sincerely. So would I say I would encourage more people to go into industry? I would say we need more great faculty, actually.
Yeah,
that's what I'd say.
I'm so happy you said that. So we've run out of time, but there's one thing I want to ask of you. I had given you a heads up that I was going to ask you for the list of 3 to 5 books or papers that you think we should all read. So I'm going to ask if you'll give us a copy of that so that we can send that out, and everybody can know that that's coming. And I apologize that we didn't have time to.
We have, and believe it or not, I had the list ready even before you asked it. So
oh, you did?
Yes. Yeah. So in other words, I do think about this, and I for me, like reading some of these papers is such a joy, such a privilege. So absolutely happy to edit that with you, Nick, and send it out to the community.
So to people that are online, I think many of you may have expected this is going to be a purely technical discussion. And I think that one of the things that I wanted to make sure that we could do was get to know a little bit more about Amin. So I want to really thank Amin for sharing the stories of your past, your story, your career path. It's been incredibly illuminating to me, and I'm sure to everybody else on this call. I will try harder next time to try and find things that we disagree on, but maybe we disagree on too much.
We'll work on that. We'll work on that. Yeah.
Thank you to Christophe and Nate for helping with the questions, and for Serge and others that helped us with organizing this. Really, really appreciate it. And I think with that, we're going to wrap up. But Christophe, any last words?
No last words. Nick, you did everything for me. Okay, I mean, it's very good to
be with you.
Okay, so I repeat the thanks to everyone. I mean, Nick, it was a great session. I'm sure it's gonna pop up in the replay. This is recorded, and so many people are already sending me private messages asking, Christophe, do you know if it's recorded, including at Google?
It's been a privilege. Thank you so much.
Wonderful.
We also have another 50 questions that we didn't have time to ask, including one in which I would have been interested in your answer. I mean, but I can always ask you. So.
We'll see. Maybe we can get them somehow. But yep, thank you.
Yeah.
It was a privilege. Thank you so much. Thank you, Christophe, and thank you, Nate.
Thanks to everyone. And now I just need 1 minute to show you the program. And I think bye. I mean. I just need to show you quickly the program of the next, which is related to one of the questions I had for Amin. We're going to talk in 2 weeks from now about internet measurement. For some coincidence, from some random reason, I am also the organizer of this session. So we will have a panel this time with 4 people talking about measurement from the home, what UCLA is doing, what MLab is doing. And we'll have Philippe Aguil, who is at Google and ex-professor from UMass, Arpit Gupta from UCSB, Henning Schulzrein from Columbia and NTIA, and Timur Friedman from Sorbonne in Paris. So with that done, thank you very much. I wish everyone an happy what is it today? Wednesday, and thanks again to Nate, Nick, and Amin for this amazing presentation. You deserve your good Moroccan dinner now, Nick.
Bye-bye. Thank you so much.
Bye.
Bye, guys.